Thanks, Ben. Thanks very much for the introduction. So this is a KPZ talk. Some of you are experts or on your way to becoming experts, but I'm going to try and go slow. I won't have much time to say much about the proofs, but I'm happy to talk about them after the talk. Okay, so the basic thing that we're talking about is the KPZ universality class, which is a general term for a collection of random growth models in one dimension or random metrics in 2 dimensions that are basically built on some kind of IID noise. So I'll give one example. And these things typically play off one another. The directed landscape is going to be the scaling limit on the random metric side, and the KPZ fixed point is going to be the scaling limit on the random growth side. Okay. So let's give an example. So everything is going to take place in the plane. And you want to look at some discrete model to start. So let me start with a Poisson process. So P is going to be a Poisson process on Z cross R. Looks something like this. So this is the picture of Z cross R, and then I'm going to have my Poisson points. So it's homogeneous, rate 1. And then I'm going to use this Poisson process to essentially define a metric. So do I have colors? So I'm going to define lengths of paths. So a path can be something like, you know, it's just going to be some path on top of this graph. So it's going to be something like this. If you want, you can allow them to go backwards. I'm not really so concerned. Okay. And the length of my path, so pi, called pi a path. The length of a path pi with respect to this Poisson point process is going to be equal to the number of left/right jumps of pi plus 2 times the number of points in the Poisson process P that pi moves through. So in this example, we've moved through 1, 2, 3 Poisson points. And we have 1, 2, 3, 4 jumps. So this path is going to have length 4 plus 2 times 3. Okay, so this is the model. And then maybe I can fit one more thing before moving up. The distance between 2 points, P and Q, in Z cross R is just going to be the minimum length of a path pi over all paths starting at P and ending at Q. Okay. And if you think about this for a little bit, you'll notice that actually, if you say wanted to find the minimum over a path starting at this point P and ending at this point Q, it's never going to be beneficial to go backwards. It's only going to be beneficial to kind of scan left and right. So a more realistic maximizing path might look something like this. So that's an example of a metric model. So it's the idea is we've constructed a metric. It's built on top of IID noise. This is not exactly a metric because if you have 2 points that are on the same line and they aren't separated by a Poisson point, then that distance is 0. So it's really a pseudometric, but that's not a very important distinction. Questions so far? All right. So there are various ways you can take a random metric and define a random growth model. The following is a reasonable idea. So this is random growth. So let me fix some point y comma s, which is in Z cross R. And I'm going to define ht of x to be the distance from the point ys up to the point x, comma, s plus t. So this is defined for x in z and t greater than or equal to 0. Let's do this. Okay. And so what you've defined here is, if you think about this, we will. So what we've defined is the way you should think of this is for every t, so t you're going to think of as time, that's going up and down. For every time t, you're going to have a function. So ht is a function from z to z for all times t. And you can notice that ht of I minus ht of I minus 1, this is always equal to plus or minus 1 for all I. So what we've defined here is we've actually defined a Markov process, right? So the state space for your Markov process is functions from z to z, which always have plus or minus 1 increments, okay? And so they're going to look something like this. And you can just check that with these rules, what happens is everywhere you see a local minimum, you flip to a local maximum independently with rate 1. Okay, so this is TASEP. Process. So you flip min to max at rate. And TASEP is kind of a classically very solvable model in the KPZ universality class. You can write down lots of formulas. This coupling gives you colored TASEP. This is the colored TASEP coupling, or it's Liggett's basic coupling, if you're aware of those things. And you can actually write down formulas for this model as well that go beyond what you see over here. Okay, so before we move forward, you can ask, well, we defined a Markov process. If you think about H0 of x, with this particular definition, I'm always starting from this absolute value function. So this is a narrow wedge. If you want to start from some other initial condition, you can do so using this framework in the following way. So you can define for a general initial condition, if you define ht of x from your initial condition f, and I'm going to specify a starting time s. If I define it like this, to be the minimum over all sites y, f of y plus this distance in the process p from ys to x s plus t, this is a TASEP started from the function f. So this is maybe I should say, if you're not familiar with this world and you don't know what TASEP is or why we've put it in capitals, don't worry about that. It stands for something, but that doesn't matter. For us, just think of it as a funny name for this particular process. Okay. So what do you expect for these sorts of models? So we're going to look at scaling. So the idea is, let's look at distances between points that are very far apart. They're sort of order n apart. So if you look at the distance from, say, the origin up to a point which is distance n apart, then what you expect is that this is equal to a constant times n. So that scales like this. And then there's a fluctuation term on top of this, which is order n to the 1/3. And if you look at the path which achieves this minimum, so this is the geodesic between the point 0, 0 and 0n, then this is going to wiggle back and forth, and it's going to wiggle on a scale which is order n to the 2/3. So these are kind of these characteristic KPZ scaling exponents. There's a similar picture that you can think about on the random growth side. So if we start with this absolute value function at time 0, then after time t, so if this function is ht, what you expect is that you've grown by a distance which is order t, and you see an interesting limiting structure in a window which has height t to the 1/3 and width t to the 2/3. And these precisely correspond to the 1/3 and the 2/3 that you see down there. So the correlations live on this 2/3 scale. Equivalently, the geodesics wander back and forth on the 2/3 scale. The fluctuations of the distance itself, or the fluctuations of the height function itself, live on this 1/3 scale. Okay. All right, so like I said, these are highly solvable models. And in particular, with these scaling exponents, you can actually take scaling limits of both of these models. So let's do this first on the height function side. So this gives you a universal, what's supposed to be a universal limit object in this class, which is the KPZ fixed point. So this is a theorem. It's due to a very U of t theorem, Matetsky, Postel, and Remenick from 2016. And essentially, I'll write it down kind of precisely, but basically what it says is that on this scale, you see a limiting Markov process. So if I look at my height function after time, which is order n, and I scale space on this n to the 2/3 scale, starting from some reasonable enough initial condition, subtract off a law of large numbers term, and rescale by this n to the 1/3 term, then I converge in distribution to some limiting growth process started from a limiting condition f. So you should think of Fn is chosen to converge to f, like our starting initial conditions are chosen to converge to our limiting initial condition f. Okay. This convergence takes place jointly over all t and all x. Okay, so this is convergence is joint in x and t. And ht, previously little ht was a Markov process on functions from z to z. Big ht is now a Markov process on functions f, which go from r to r, and I'm going to allow the point -infinity just because, for example, this absolute value function, when you scale it in this particular way, converges to something which is just a delta spike at 0 and is -infinity elsewhere. So, and I'm going to specify that these functions are upper semi-continuous, though the moment you start to run time for a little bit, the functions become continuous. So you can start with an upper semi-continuous initial condition, but then the moment you do that, you will hit a continuous function. there's some rules about, the growth of these functions at infinity, but let's not worry about that. Okay. Let me call this class. I'm going to call this class UC, upper semi-continuous functions from R to R union negative. Okay. How about on the random metric side? You have the following limit theorem, which is due to Agarwal, Corwin, and Hegde. And it's 2024. Okay. What it says is that if you basically apply the same scaling, not on the growth side, but on the metric side, then you also see a scaling. So I'll just write it down. X n to the 2/3, 2ns. So y n to the 2/3, 2nt. Subtract off some law of large numbers term. Scale by negative n to the minus a third, just like we did before. Then you converge in law to a 4-parameter function, L of x, s, y, t. And this is what's called the directed landscape. And it is a 4, so this convergence here is taking place jointly in all 4 parameters, okay? And the function L is, it's a random continuous function from, essentially from R4 to R, but I'm going to write it as directed R4 with this arrow. So this is just going to be the set of all x, s, y, and t in R4, such that s is less than t. Okay. So in order to take a reasonable scaling limit, directionality needs to pop out in the limit. So we started with a potentially undirected setup, in that we could look at distances where we interchange the role of s and t. But when we go to the limit, in order to see something which still behaves like a metric, that still satisfies the triangle inequality, we need to subtract off some giant slope which forces directionality upon us. Okay. Okay. So this theorem, I should say, is for this particular model. The directed landscape is something that myself and János Ortman and Balint Virak had actually constructed. We constructed it a few years earlier, I believe it's 2018. Okay. And proved that it was a scaling limit for some other model. So the point is that beyond this Metetski-Guasel-Remenick theorem, since this paper, there have been, a handful of a variety of models with different levels of solvability, some comparably nice to TASEP, some nowhere near as nice, where we know KPZ fixed point convergence. And there's kind of a similar story on the directed landscape side. One thing I want to point out about this is you'll notice there's a big difference in the dates. There's 8 years, and that's because it's not, there's a genuine extra difficulty to go from the growth side to the metric side. So this is a non-trivial thing. And the way that it's typically done is you use some extra combinatorial structure. Up until what I'm talking about today, all the examples that I know of, all the ways in which people have been able to do this is you use some extra combinatorial structure coming from like the Robinson-Shenstedt-Knuth correspondence or Yang-Baxter, which gives you access to these sort of statistics. Okay. And maybe just to finish, okay, so like I said, it's typically much harder to go from, it's typically much harder to get a metric scaling limit rather than a growth scaling limit. But once you have the metric scaling limit, the growth scaling limit actually falls out as a marginal. So just like we have this variational formula connecting TASEP and that metric, we have a similar variational formula connecting the directed landscape and the KPZ fixed point. So if you want to look at HT started from some location, started from some initial condition F, then this is a maximum over all y. f of y plus L of, say, y0, or something like this, ys x s plus t, something like that. I've made a small sleight of hand as well, which is that I've introduced a negative sign here. Ignore it. It means that instead of getting a metric in the limit, you get something which satisfies a reverse triangle inequality, but morally everything is the same. You just have to look at it upside down. It's no problem. Okay. Okay, so the goal of this this work with Ling Fu was to develop basically a systematic way to get the directed landscape if you only know that you have the KPZ fixed point. So in other words, the goal is to find some characterization of the directed landscape, which would make this sort of theorem essentially immediate. Okay. And you can think of this as some, like in the broader context, this is something to do with universality, that there's like this, that all of these KPZ limits, like if you have some general conditions which put you in the KPZ universality class, then you should be able to get everything. Okay. So this tells you that if you can get like 99% of the way to the end, then you can get 100% of the way to the end. That's how you can view this. Well, let's write down the characterization theorem. And to distinguish it from the Agarwal-Core and Hegde result, I'm going to say late 2024. Colored Tasib was actually our original motivation for trying to do something like this. But when we found out about their result, we had to work a little bit harder to include a bunch more models of applications. So okay, so we're going to assume we have a function which, again, goes from this parameter space directed R4 to R. Suppose that this is a random function satisfying a few properties. One, we have KPZ fixed point marginals. So what this says is that what we're going to say is if you fix any point P in R2, let's write it as fix any point XS, then the function y comma t maps to L of XS y t plus s is a KPZ fixed point from the delta mass at y. So this is just this function, which is equal to 0 if z equals y, and negative infinity else. So you'll notice that this is the way in which the directed landscape encodes the KPZ fixed point. So thank you. Yeah. Otherwise, it presupposes the theorem by notation. So we're assuming that it has this property with KPZ fixed point marginals. And you can just check that this is exactly what you get when you plug in the simplest possible function for f there, which is just 0 at a single point and negative infinity elsewhere, which just kills the maximum and replaces it with this simple function. Okay. 2, independent increments. So if you look at If you look at this, these types of functions, so if you look at the distances defined in M from time Si to time Ti, or a bunch of these times, these are independent when the intervals you're working with, Si, Ti, are disjoint. Okay. It's a very natural assumption. If you go back over here and you think of the sort of metrics that we start with, these are metrics where we're going from, where we move between, where we're using independent noise in disjoint parts of the plane. And we have this directionality in our paths, which means that that independence will basically always be carried into the limit. And the final condition is a triangle inequality, which is going to say for all P, Q, R, and R2, M of PQ plus M of QR is less than or equal to M of PR. In other words, that in the limit, we have a metric. Okay. Again, notice the reverse triangle inequality if you're not familiar with it. But that's all you need, and then you have a directed landscape. So that's the main theorem. Maybe I'll make a comment. I'm not going to really have any discussion of topology or topological considerations in the talk. In practice, the way we state the theorem in the paper is you replace directed R4 with, say, like all rationals in directed R4, so directed Q4. And then you don't need to worry about topological constraints. And then the conclusion would say then M has a continuous extension, which is a directed landscape. So if you are, out in the real world and you have some model where you don't have to deal with tightness issues and such, that's better suited to working with that. Maybe why don't I say then M is equal in distribution to this limiting object L. And that's what it means to be a KPZ. Yes, yeah. So this is like, in other words, this, yeah, maybe I can write something like this. This is equal in distribution to H T of Y started from the appropriate narrow wedge condition delta X. Okay, any other questions so far? So I'm not going to state, I'll state, kind of corollary you can get out of this. Basically, if you have an IID metric model, kind of like the colored taste that we started with, and you can prove that it has KPZ fixed point marginals, properties 2 and 3 are typically trivial to check for these sorts of models. And so the corollary is any such model will converge to the directed landscape. So various IID models, IID metric models converge to the directed landscape. And some of our favorites, well, there's this colored T-sep that I mentioned. But if you like last passage percolation, any solvable last passage model where it converges to the KPZ fixed point, you can again get landscape convergence from that. So if Balint were in the audience, a model he likes a lot is the random walk web distance or the Brownian web distance. So these fit into this framework because you have a connection with Brownian last passage that gives you KPZ fixed point marginals. So
But just for like case out, this gives a much simpler proof than Gregory.
Yeah, so I mean, you know, this gives a proof for TASUP that I would be like 15 pages, and that one gives a proof which is maybe 150 pages, to give you a sense of this is quite an involved theorem if you try and do it from scratch. But I mean, though in truth, like if you knew this theorem already, like what I'm saying is the proof of this is 15 pages. If you knew this theorem already, then the proof for colored TASUP is like 3 sentences, just to because you need to say some words at some point.
So I don't understand why it's so much. I mean, so much simpler. Here, you've got to have your hands on the object. So you've got to prove there's a living object before you can use this to identify.
Yes.
So that part hasn't gone away.
Yeah. So maybe I should say this is not the way we wrote the paper, but if you want, you could use this framework. So proving tightness is kind of a known thing, and once you have access to KPZ fixed point marginals, tightness is not really a big thing. If you wanted, you could kind of reframe this theorem and construct the directed landscape this way without going through the stuff that we went through 5-6 years ago. Exactly. Yes. So we could do. We haven't written it that way. We thought about doing that. It's a little bit of a pain, so we didn't. Okay. So the other thing you might, another thing you might be interested in is what if you have some random growth model and you don't know if there's a natural geometry sitting underneath it. Like you can't define an IID metric model with geodesics, which gives rise to that growth model. And so we have a theorem, which is in essence really just a rephrasing of this other theorem, which deals with that case. So so this is you can think of this as let me write down the theorem and then I'll say some explanation. So suppose we have a family of operators, and again I'm going to be really fast and loose with topology and just ignore it completely. So suppose we have a family of random operators. Let's call them KST. And they go from our function space UC to UC, indexed by S less than T in R. You can replace this with Q if you want to, such that they satisfy the following conditions. So 1, this is kind of a KPZ fixed point. Basically, what we're saying is we have some coupling of, the first condition is going to say we have a coupling of the KPZ fixed point simultaneously for all initial conditions and all times. So KSTF of dot is the same as the KPZ fixed point run for time t minus s for all s, t, and f. 2. This is essentially saying this is going to be like an independent increment condition. Another way you can think of it is this is going to say essentially that your coupling is jointly Markov. Okay, so KSI for I equals 1 to K are independent if SITI are disjoint. So any natural coupling is going to satisfy it. It's hard to come up with. I mean, it's possible to come up with couplings that don't satisfy this, but they're a little bit weird. You really shouldn't think about them too much, unless you have, some good reasons to, I suppose. 3, monotonicity. So for all s less than or equal to r less than t, I should say this is s less than or equal to t. We have the following thing. So if you have 2 initial conditions, G and F, and if I have the following thing. So suppose I run my KPZ fixed point under F forward to time R. So suppose when I do that, it dominates some other initial condition, G. Then, if I were to continue running this forward all the way to time t, it will dominate my KPZ fixed point from G, run from time R to time t. The very, again, kind of a really natural property for your couplings to have. If you have never done this before and you like the colored Tay-Sep coupling, you can just check that this is true for the colored Tay-Sep coupling. Maybe I'll mention another thing, which is that I've set this up for 3 times. Alternately, you can basically replace this condition with the following pair of conditions. One which would just say that if you have 2 initial conditions, one of which dominates another, then when you push them forward by the same amount, that domination holds, plus the fact that these Ks together form a semigroup. But in practice, the semigroup property is a bit annoying to pass to the limit, so we set it up without that. Not yet. There's going to be a 4, and 3 and 4 together give. So 4 is, again, something that is really, I don't think it's, 4 is also very natural, just shift commutativity. And what this says is that for all F in UC, S less than T in R, and for every constant C, if I run my KPZ fixed point forward from an initial condition F, and then I add to it a constant, then that's the same thing as running it forward from the original function shifted up by a constant. So again, a very natural initial condition, a very natural condition, and then I should always write a theorem. I tend to get to the end of these assumptions and then think I should just be done. But so then there exists a directed landscape L such that for all F, S, T, K, S, T, F of X is equal to this variational form over there, max over Y and R, F of Y plus L of XS, plus L of YS XT. So in other words, if I give you any coupling of the KPZ fixed point, which is basically Markovian, monotone, and shift commutative. So it's a grand coupling in the sense that I'm simultaneously coupling all initial conditions. I'm also coupling them simultaneously for all times. And I have 3 very natural properties, which essentially in every pre-limiting model I know these hold, or you expect them to hold. Then you see a directed landscape. So in other words, just from the existence of such a coupling, there emerges a metric with geodesics. So even though there's many pre-limiting models where there are pre-limiting growth models where you don't see a metric with geodesics giving rise to these models, and you don't have this sort of variational formula, if you take a scaling limit, all of this structure has to emerge in the limit. Okay?
For example, I guess KPZ equation.
Yeah.
Now it's obvious once you bridge to the fixed.
Exactly. Yeah. So you can. This is going to be one of my corollaries. It's like, so these are very natural. These are very natural properties to check for the KPZ equation. I mean, this is by definition, and this is by almost, like most often these two are by definition. I will say I think it's not very natural to remove property 2 or property 3. There are reasonable couplings of the KPZ fixed point, I think, that do not have shift commutativity. And if you take away shift commutativity, this theorem definitely fails. And I think there are interesting limit objects there. But that's for another day. But there's some interesting directions there if you get rid of this. Okay. So let's just list some corollaries. So things like the KPZ equation, things that aren't obviously kind of metric models, so colored ASEP, non-nearest neighbor asymmetric exclusion, which we have something which we call exotic ASEPs. So there are sort of exotic couplings of the asymmetric simple exclusion that are kind of fun, that we cooked up that can go into here. O'Connell-Yor polymer, all of these converge to the directed landscape. So if you're familiar with any of these or you like the names, just to convince you that you can do a lot with this sort of theorem. Okay, how much time? So a little under 10 minutes. And the thing that I'll do that there's, so I wrote up two theorems. The proof at theorem 1 is actually not so long, but a little bit too long to explain in 8 minutes. The proof of theorem 2 from theorem 1 is really quite straightforward. So I'm not going to do everything, but I can kind of give the structure, just so you can see how the metric is going to arise from this stuff. So this is theorem 1 implies theorem 2. And just so that I want to distinguish the types of bullets, so I'm going to give these ones a double circle. So let's define. We're just going to guess what our directed landscape is using this formula. So let's define L of ys xt to be the KPZ fixed point started from the delta spike at y, evaluated at the later point at x. So of course, this needs to be true for us to prove the theorem in the end. And then when you do this, you can just check that 1, 2, and 3 hold. So the KPZ fixed point property 1, not completely immediate, but it essentially corresponds to the double circle 1 on the landscape side. The Markovian property for your coupling essentially corresponds to double circle 2. I'm definitely doing some things that are a little bit not completely obvious, but morally it's there. And then you can do a little quick computation to check that 3 and 4 give you the triangle inequality. So 3 and 4 together give you the triangle inequality. So let's check this for this third one. So let's let xs, yt, zr be points in R2 with s less than t less than r. Okay, so we're going to try and prove the triangle inequality. So let's write down one side. So if I look at L of xs yt plus L of yt up to zr, then I can define this in terms of my k. So this is simply k going from s to t of a delta spike at x evaluated at the location y plus k going from t to r of a delta spike at y evaluated at location z. Okay. So now what I'm going to do is I'm going to apply shift commutativity. So I'm going to think of this as a constant and bring it inside my initial condition. So this is equal by property 4 to k going from t to r of delta y plus kst delta x of y. Thinking of this second part now as a constant, all evaluated. That's that. Okay, but now let's think about what this is as a function. So if you look at delta y plus kst delta x evaluated at y, this is simply the function. So if you think of this as a function and evaluate it at some location w, then this is equal to negative infinity when w is not equal to y. And otherwise, it's kst delta x of y. And so in particular, the whole thing is dominated by the function kst delta x, because they're equal at y and the other one is negative infinity elsewhere. So now, if you think about it, you're exactly in this setting where your g is this guy in here and your f is delta x. Okay? So then this is less than or equal to what happens when we would have pushed f forward starting at our original time. So this is less than or equal to k SR of delta x evaluated at the point said. And just unpacking that, that is LSX. LXS is at R. XS. So you can really think it's they're one and the same. So shift commutativity plus monotonicity, you can see very clearly where we use them, and then that gives you the triangle inequality. Okay. Any last questions? Otherwise, I will. Yes.
So these properties here, do they imply a K is a semigroup or no?
They do. They do imply that. I mean, so you know, if you want, once you're down here, you know that K is a semigroup. But the fact that they imply K as a semigroup is not. It uses the fact that you have KPZ fixed point marginals. So if you were to, I mean, it's quite natural actually to just assume that K is a semigroup. But if you want to use this kind of theorem in practice, it's actually quite hard to pass the semigroup property to the limit, because if you think about what the semigroup property in the limit would say, it would say that the semigroup property holds not in the prelimit, but it would say that if you have some like approximations of where your function is at time 1/2, then that approximation matches where it actually is, or something like that. It's kind of a little bit of a technical point. And so it's easier to work with this form because monotonicity and shift commutativity are typically immediate to go to the limit. Exactly. Yeah, so there's lots of stuff in here which is using the fact that we have, so there's lots of things underlying the proof that I haven't mentioned, which use the fact that, for example, if you have two objects and they're equal in distribution and one dominates the other, then they're equal almost surely. So there's a lot of things that kind of like small arguments that happen in the background. And one such argument gives you the semigroup property. Yes. I mean, you can apply this. Any model that I know of, you can just apply this to this framework too. We managed to cook up. So we have these exotic A-subs. We managed to cook up. So here, let me give you two couplings of T-sub. So one is which both fit into this framework very nicely. So one is the colored T-sub coupling, which is you have. I'm going to switch to particle systems, even though I haven't used particles yet, which is all the sites ring together in your different copies of T-sub. When a site rings, it rings for all your T-subs together. There's also the particle coupling, which is all your particles have labels and particles both ring together. Both of these together fit into our framework, and you can prove convergence to the directed landscape for these couplings. Now, and actually both of these are solvable models. Now you could ask, here's a natural thing, which is you attach clocks both to the particles and to the sites. And half the time, and they're each rate 1/2 instead of just sites being rate 1. So that's still like a nice coupling of TASEP. And I believe it's one of the few examples that it was the only example that we cooked up where we couldn't actually get shift commutativity to hold. That and kind of variants of this. Yeah, you can do low gamma. Like anything like this is any model that you can. I mean, I'll make a bold statement, which is probably wrong. Any model you can find that someone's actually written down instead of us trying to cook up counterexamples, I think you can do. It's really like you have to try to cook up counterexamples to this stuff. I should say there are examples where I can cook up an example satisfying 1, 2, and 3, which doesn't satisfy shift commutativity, which should have a different scaling limit. So there are interesting different scaling limits. So I can go into them if people want, but yeah, I can give an example. So okay, here's the example. Okay, it's going to be we're going to define. Okay, let's define a hotel. The hotel is going to have infinitely many floors, and there's going to be a Poisson point process on every floor. So infinitely many copies of R2. So it's like Z cross R2, and you have a homogeneous point process independent on every floor. Okay, and what you're going to imagine is that each of these Poisson points is a ladder which takes you to the next floor. Okay, and so you are going to imagine someone can start at some point in the hotel, which start at some like spatial location, and making only steps that take them up or to the right. You can ask how far could they possibly climb, starting at spatial location 0, 0, ending at spatial location n, n. And the maximum height that they can climb to, or generally like the maximum like interface that they can climb to as you vary their endpoint, that's a KPZ fixed point, because this is just PNG. But this is very clearly not shift commutative. And if you think about it for a little bit, you can pretty quickly guess that there's going to be a completely different type of scaling limit. It's a bit more like it should be some kind of analog of like a Brownian web, but for the directed landscape. And when you get rid of shift commutativity, basically what you'll have is some function which, instead of being a 4-parameter function, it's a 5-parameter function, which is like a web height parameter. So things should exist. I'd be interested in constructing them. Yes.
It goes from geometry to
do you have an example? I mean, no. Like the point is,
saying that there is only one metric which is compatible with statistical geodesics.
So what I can tell you what I'd really like, what I'd like to be able to do would be something like, rather than assuming KPZ fixed point marginals, assume something which is like really not nearly as solvable a condition. Like assume that you have the Brownian motion is stationary, but you have all of this metric structure. And maybe you upgrade it. So like, don't worry about just having triangle inequality. Allow yourself to actually have geodesics. So having this be like a metric composition. Then could you get? Oh, yeah. So this is like I said, this is like pushing from the 99% of the way there to 100% of the way there on universality. I'd like to be able to kind of pare back as much as possible. We thought about it. Everything I tried in terms of weakening the assumptions didn't. Well, okay, there's some things like originally our characterization had that you actually had to have geodesics rather than just a triangle inequality. And so we've been able to pare back some of this stuff. And in terms of paring back the exact statistic condition, I never succeeded in doing that, but I'm interested. I'm continuing to try.
They have to look at like an plus 2.
Yeah, that you can do. But yeah, that you can do. Yeah. So but that's somehow much more essentially that's essentially how we originally constructed the directed landscape. But it's again, it's kind of like a different type of solvability. Yeah. But and even if you do it with like the Brownian characterization they have, it doesn't take you away from solvability in the sense that if you have a growth model, or if you have like a metric model where when you pass through RSK or Yang-Baxter or something, you get something that's actually nice and has some reasonable Gibbs property, that's supremely a solvable thing. So it's yeah. I'd love to get away from solvability just by a little bit.